All right, so today we're talking about alternate forms of the derivative. You all know what the derivative is, pretty solid on that. Gives you the slope of the tangent line. And we know right now the classic form of the derivative. What we're going to do is we're going to look at some slightly different forms of the derivative, some slightly other limit type statements that also allow you to get at the derivative, and also some alternate forms of what it looks like when you evaluate the derivative at a point. So we know the derivative in general is the slope of the tangent line at here, here, here. It's like a formula. And we're going to find some different versions of that. So here we go, just as a reminder. This is the classic form of the definition of the derivative. It's what you already know. That is f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And what we've discussed before is what it is. It's literally the slope of the secant line, but then you take the limit of that as your distance between your 2 points approaches 0. Okay? And the picture that goes with that should be some function comes along here. You have x and then some delta x, which is steadily decreasing. And obviously at this point over here will be x plus delta x. In some textbooks, they have h. They say the limit as h approaches 0, and then up here we have f of x plus h, and then minus f of x all over h, where just literally h is that distance rather than delta x. I do kind of like that because you just have one variable, and as a general rule, students tend to be more comfortable with just one variable rather than, it's one symbol rather than 2 symbols together, but y'all can handle delta x together as a symbol. So I'm not really going to stress over that. So that's a classic form, I should say. Of a derivative, or of, we can see the derivative function. So known as f prime of x. We can, it's, when you have x squared, then you're going to have 2x. The derivative is 2x. You get a whole function. The classic form of the derivative function at a point. We'll say of the derivative evaluated at point C is f prime at C equals the limit as delta x approaches 0 of f of C plus delta x minus f of C all over delta x, pretty much same sort of thing. And your picture is going to look almost identical, with the exception, instead of having some generic x here, we have a quasi-generic c. We have c right there, and then the distance between that and the other point is delta x, so therefore this is c plus delta x. And you've got, so it's still the, well, you know what I should do probably. it's sort of like we're finding the slope of that, of the tangent line exactly at that point. Not the best picture. You get the idea. Okay. So what I'm going to show you now is what's known as the alternate form of the derivative evaluated at C. So it's f prime of C equals the limit, and this is where it gets weird, as x approaches C of f of x minus f of C over x minus C. So it's still the same picture, still the same idea. We're wanting to know what is the slope of the tangent line at that particular point. But the way that we're finding it, rather than having, C plus a delta x, is we're picking some arbitrary x value over here. And then notice what this is. F of x minus f of C over x minus C. What does that look like? Minus over minus
Like the slope formula?
Yeah, it's the slope formula. Yeah, it's the slope. It's the slope of 2 points. y2 minus y1 over x2 minus x1. And that's exactly what this is. It's literally just saying what's going to happen to the slope as x approaches C. So as x gets closer and closer to C. It's really just another way of saying what would happen as that delta between them, the delta x, approaches 0. So I could talk about the same thing if I'm approaching Rigel, okay? You could say, as Mr. Goddard approaches Rigel, okay, we'd see that, hey, Rigel. Or we could say, as the distance between Rigel and Mr. Goddard approaches 0. Still the same thing, right? Still getting those two. And what we're doing is we're finding that that's what the limit part is taken care of. And this is the slope of the secant line. So that's going to, what we're going to do is we're going to see some problems today that are going to look like this or like this or like that. And what we need to understand is even though the problems that we look at appear to be limit problems and we're like, oh, we're back to limits, they're really not, okay? What they really are derivative problems that are sort of disguised as a limit problem. Let me show you what I'm talking about. So here's an example. What if I said, find the slope of the tangent line to f of x equals 5x squared at x equals 3. Find the slope of the tangent line to f of x equals 5x squared at x equals 3. What would be the first thing that y'all would do?
Find the derivative of x.
Find the derivative of x. So that's no big deal. So f prime of x equals, we'd apply the power rule. So 10x substitute in 3, so f prime of 3 equals 10 times 3. So 30, right? Okay, so what if I add, great, that's our answer, we've done what we said to. What if I added this set of instructions in the middle? Using the definition, or using the limit definition of the derivative. What in the world? Okay. Well, I can't just say f prime of x equals this. What I would have to do is I'd have to write something like this statement right here, where I could say f prime evaluated at 3 equals the limit as delta x approaches 0 of f of 3 plus delta x minus f of 3 all over delta x. Y'all understand? What we've got going on right here is essentially the same thing that we have down here. It's f prime of 3, but it's got the limit form, and we'd have to apply some different limit properties and things like that to evaluate it. If I were to expand this real quick, so f prime of 3 equals the limit as delta x approaches 0 of, and then I put, was it 5x squared? So 5 times 3 plus delta x squared minus 5 times 3 squared all over delta x. And then we could go through and we could multiply everything out and we could factor and we could go on and we could eventually get to the proper answer. I'm not going to expect you to get to the proper answer. The type of problems that I'm going to be giving to you are actually I'm going to give you this. I'm going to say, what's the limit as delta x approaches 0 of 5 times the quantity 3 plus delta x squared minus 5 times 3 squared all over delta x? What does that equal? What does that evaluate to? But more importantly, what is the function that this is an expression of the derivative of? Let me say that again. I'll give you this, what's inside the box, and I'll say, what is the function that this is showing the derivative?
As in like 5x squared?
As in 5x
so
squared.
So we need to look at that and recognize where the x should be.
Yes.
Okay.
So you look at this and you say, I've got blah minus blah over delta x. Okay, so this is 5 times blah squared, and over here we have 5 times 3 squared. Okay, I kind of see a pattern between those two. It looks like the original function is 5x squared. And then the follow-up question is, at what point? How do you know 3?
Because that's what it fills in.
Yeah, we see a 3 right there, and we see a 3 right there. So we would say x equals 3. And then, what's the answer? And to do the answer, we actually go back over here and say the answer is 30. So I'm not going to expect you to be doing all sorts of limit algebra. Okay, I'm going to give you this sort of complicated limit statement, and I'm going to want you to recognize it essentially as either this form right here, the alternate form, or the classic form. of the derivative, and you need to know that when that's the case, you're going to have the function evaluated at c plus delta x minus function evaluated at c over delta x, or you're going to have f of x minus f of c over x minus c. Okay? At this point, it's best just to give you some problems and go from there. Alright, so we're told here that the given limit is in fact a derivative. The questions are, what's the function, what's the x value that it's expecting it to be evaluated at, and then go ahead and do the actual calculus on it. Now if you look here, as you can see, you've got the h instead of the delta x, no big deal, okay? So if the limit as h approaches 0 of 0.25 times 3 plus h quantity to the fourth minus 0.25 times 3 to the fourth all over h. So, class, looking at that limit and knowing what the templates are, what appears to be the original function here?
0.25 x.
Yeah, 0.25 x to the fourth, great. What appears to be the x value at which it is being evaluated? Yep, 3. So, what this limit problem is doing, it's asking us, really, find f prime of x evaluated at 3. So the way that we're going to do that is we will over here write f prime of x. So 4 times 0.25 is 1, so 1x cubed. And so then f prime of x would be, or sorry, f prime of 3. 3 cubed, 27. So, I think y'all, if I were to say, how did y'all get the 3? You'd say, well, we saw that it was substituted in there as the x plus. How did you know that it was 0.25 x to the fourth?
Because inside the parentheses is what x is.
Mm-hmm.
And so that's just, you just change it to x.
If you change it to x, then it's pretty, yeah, it's pretty obvious there. Okay, let's look at this next one. The limit as h approaches 0 of 3 times 1 plus h minus 3 all over h. That's kind of interesting. Anybody want to guess what is, or make a suggestion, what is f of x?
3x.
3x. Ooh, okay. This one. Well, if that's the case, I put an x equals 3 here. I probably should have put c. What value? Well, what's the value that this one's evaluating on, Gracie?
1.
What they don't show you is that there's like an invisible 1 right there. But that makes sense, right?
Mm-hmm.
Because if you say that, then you're like, ah, okay, because it's 1 plus h, and so therefore it's really 3 times 1. So sometimes this term over here will be maybe simplified or whatever, but we can handle that now. So Harley, what is the derivative function?
3.
You're correct. And now this is weird. What is f prime evaluated at 1? James?
3.
It's 3. Because f prime of x is 3. So the derivative is always 3. So it's the derivative evaluated at 1. It's the derivative evaluated at 5. And so on and so forth. Okay. go ahead and try the next one or two as a table. Any problems that we don't solve here together will be your homework. Gracie, you gonna answer number 3?
Sorry, number 3.
Yep, looks good. Alright, Ivan, thanks for watching.